11.1 and 11.2. So tell me what you did.
We measured 50 grams of salt.
Yep.
And put it in like a little
Beaker.
thingy. Yeah. And then we got some hot water from that.
Yep.
And then we combined them, and then we stirred them, and then we put it on this thing until it got to 95 degrees Celsius.
Mm-hmm.
And once it did, then we made a funnel of the filter paper.
Yep.
And then put it over this was what it was in, but then we put it in a little one. Then we filtered out all the salt, and then we put it in the freezer.
All right. So this in here is salt water, but it's hot salt water. Ooh, where's my? There it is. Okay, so I don't really see any salt in there currently. So there's 2 in there. All right, so hot water, made a saturated solution in there. And now we're going to, so we're testing the solubility of a solid in a liquid. And now we're going to fill up some beakers with some soda, and you're going to test the solubility of a gas in a liquid by sticking it in cold water and hot water. Ready, go.
Okay.
All right, you got your soda. You're going to come over here and you're going to stick one in the cold water, and you're going to stick one in the hot water, and you're going to see how the bubbles react.
Does this one help?
Yep.
I should probably.
Yeah, you might want to use the. So this is the bubbles are the gas that's in there, and
Your bubbles are.
check out your bubbles. I can't really see them. What's happening to your? There we go. Which one has bubbles moving faster? All right, switch them and see if you. So now that one's cold, but as you heat it up, oh, look.
You need this.
And can you get yours to slow down? Are yours slowing down?
Yeah.
All right.
There's
Okay,
like no
and then if
bubbles
you
in
want, you can switch them back. So which one do you think holds the gas better? The hot water or the cold water? If you want carbonated soda, do you want to keep it cold or do you want to keep it hot?
Hot?
You want all the carbonation to come out of it.
No.
See that all the bubbles coming up is
Keep it-
all that's
so-
all of your gas
oh.
coming out. So what's going to happen eventually to this? Is that going to be carbonated soda anymore? No, all the carbonation's going to come up. So which one holds the carbonation better, cold or hot?
Cold.
Yes. So if you go ahead and let the boys do theirs. So if you want your soda to stay carbonated longer, should you have it out on the deck in the sun, or should you maybe keep it in a cooler insulated cup?
Yeah.
All right. You see any bubbles moving up in your
I do.
yeah? Lift it up so I can see. Wow, check out all those bubbles moving up. Do you have any bubbles moving up in yours?
No.
All right, trade. Put the hot and the cold and the cold and the hot and see if you see a difference. Hopefully you don't burn your hands.
Oh yeah.
Alright. So what did we see? What did you see?
And with the experiment.
In the I can try to shut that off. The soda one.
Oh. We saw the carbonation leaving when it was in the hot water.
The carbonation leaves in the water. So solubility rules for gases is as the temperature goes up, the solubility of the gas, that means the solubility is how much it can hold. So if I want a lot of gas to stay in my liquid, I want to cool it down. As I heat it up, as the temperature goes up, the solubility goes down. That means it can't hold as much gas in a liquid. If it is hot, all your gas goes, I'm out of here. But if it's cold, it can hold it longer, which I know none of you like drink alcohol or anything, but whenever you watch a football game, we won't talk about the Packer game. But whenever you watch a football game, they always have those beer commercials, and there's Coors Light, and they pay extra for refrigerated trucks. Why? They cold process it. Why? That's a lot of money. Why? Because it holds the carbonation better, and apparently that makes it taste better, right? So they pay a lot of money to keep the carbonation in, so it's fresher for you. Same with your drinking your Sprite, Coke, whatever soda you drink. Soda you drink, the carbonation stays in better when you keep it cold. So if you want a nice carbonated drink, you want to keep it ice cold. Once it sits out for a little bit, my mom used to give me flat soda when I was sick, like Sprite that has no carbonation, and somehow that makes me feel better. I don't know, it tastes terrible, but that's what she would do. So she'd leave it sit out or warm it up so that all the carbonation would come out. So as the temperature goes up, the solubility of a gas goes down. Alternately, as you raise the temperature of a liquid and you put a solid in there, like our salt that you did to the first one, what you did is you made a saturated solution. A saturated solution means it's holding as much liquid, as much solid in there as possible. So you heated it up, you poured it through the filter paper, and then what's left in there should have looked fairly clear. And you shouldn't have seen any solid salt in there because it's all liquid, it's all dissolved, and it's holding as much salt as possible. Really, we had a lot of salt in there that you pitched out, so it's a saturated solution. Once you cool it down though, the solubility of a solid, as you cool it down, the solubility goes down. So it's inversely proportional. If you want a solid to dissolve in your water, you heat it up. If you want a gas to dissolve in your water, you cool it down. So if you want to get rid of the salt in your water, you would cool it down because the solubility goes down with the temperature. So later on, we'll check our little water in the freezer, and you should see a layer of salt in there because it can't hold as much salt when it's cold. So if it's a solid, as the temperature goes down, your solubility goes down. Okay? So, and a liquid, though, liquid doesn't matter. So if I heat it up, if I cool it down, your liquids, it's either dissolves in there or it doesn't. So solubility is the amount of solute that can dissolve in a given solvent. Solute is the thing you're dissolving in. Solvent is what they're dissolving it into. So in ours, the solvent was the water. The solute was either the salt or the carbon dioxide, I guess. Carbon monoxide? Carbon dioxide in your soda. So the solubility depends on what you're dissolving in, gas, solid, liquid, and what you're dissolving it into. So we made a saturated solution of salt, and what comes out of there I'm ruining your lab now, but you should see some salt come out of your water in the freezer. And what comes out is your precipitation. So when I'm mixing things together, if something comes out in the bottom, sometimes when I have an acid and a base, the salt that comes out is called the precipitation too. So anything you have left at the bottom is your precipitation. So you have more precipitation in cold solvent than hot solvent if you have a solid dissolved in there. And again, your salt was your solid solvent. Okay, so page 362 says, for solid solutes, when you're dissolving a solid, solubility increases with increasing temperature. So they're going to ask you questions on the test about, you put some solid into a liquid, how do you get it to dissolve? Heat it up. You put some gas into a liquid, how do you get it to dissolve in? Cool it down. So they're going to give you little different scenarios, and they're going to say, you heat it up, you cool it down. But if you have a liquid, how do you get it to dissolve? Doesn't matter. So the temperature doesn't matter. Okay? So, but now pressure does matter. So if I was able to increase the pressure of something, increasing the pressure increases the solubility of gases. How do you know this? When I open this, it goes, right? And I can only do it once because I can't put the pressure back in there. When they're bottling this, they do have a way to keep the pressure in. But once I let that pressure off, I can't do it again. Okay, so if I can increase the pressure of gas, I can make more gas go in. But the pressure doesn't affect if it's a liquid or a solid. So it wouldn't matter if I increase the pressure of my salt water over there. It's not going to matter. Temperature matters, pressure doesn't matter. But for gas, pressure can matter. I can make a gas go in if I increase the pressure. So if I want to dissolve a gas better, I'm going to either increase the pressure or decrease the temperature, which is why your commercials talk about cold processing. So, and it costs a lot of money. Those refrigerated trucks cost a lot of money. So it's worth it to them, I guess. Okay, what else do I have to tell you today? All right. Figure 11.3. Actually, we'll do 11.1 too. Let's see. A chemist wishes to, because we have, I guess I have 15 minutes. Here's my 11.3. I'm looking for a picture, I guess. Okay. So here we have 11.3 is water dissolving sodium chloride. So I'm supposed to tell you, okay, last chapter we talked about something if it was polar or polar covalent or ionic or purely covalent, remember that? And polar covalent things, that means they share charges. But if it's polar covalent, you have one side that's kind of positive and one side that's kind of negative. And so those things dissolved in other things that were either ionic, because those have positive and negative charges, or something that's like water that's can be also polar covalent. So the reason why is when I have salt is sodium chloride. So what happens when I dissolve it into water, your positive side, your sodium, and your negative side actually break apart and they get surrounded by the water. So that's why it dissolves better. So your charges is actually what helps things dissolve. But if I have something that is purely covalent, or it doesn't break into different pieces. So because it doesn't break into different pieces, because of charge, they state this pH3, it still stays in one piece. So each chunk is surrounded by water, each molecule is surrounded by water, but it doesn't break into a bunch of pieces. So it won't be affected as much by temperature and different solubility rules. So if it breaks into a lot of different pieces, like sodium and chloride has a positive and a negative side, and it breaks into two different pieces, the more pieces I can get something to break into, it will affect how I can either raise the temperature, we'll talk about that, it increases the heating of something, the boiling point elevation, and it can also decrease the freezing point, which is why when I have an ice storm, what do? I go out and sprinkle salt, right? Why? Because salt breaks into two pieces. You don't know this, but it does. It breaks into two pieces, and because of that, it lowers the freezing point. So it melts the ice. And they should even sell different things that are more expensive than salt that melt it even better because it breaks into 3 pieces or 4 pieces. So the more pieces you get something to break into, the lower your freezing point drops so it can melt stuff easier. Or when I'm cooking pasta, I sometimes put salt in. You probably thought it was for flavor, and it is kind of, but did you know that it also raises the boiling point of the water? So it makes it boil faster, boil better, I guess you should say. So adding stuff to a solvent can affect the freezing point of it and the boiling point of it, depending on how many pieces it breaks into. And we'll talk about how to figure out how many pieces it breaks into next time. But just keeping, this pictures kind of help you to see that it breaks into different pieces. Okay, let's do, you're going to want to remember the solubility rules for solids are different from gases. Liquids aren't affected by temperature. So make sure when you're writing up your lab, we did 2 labs, you only have to write 1. Make sure you tell me, if you write the first one, 11-1, tell me that you made a saturated solution. Tell me how the temperature affects the solubility. So as I heat it up, it increases solubility. As I cool it down, it decreases solubility. If you're going to do the other one, make sure it's talking about gas. Make sure you tell me that as you heat it up, you decrease solubility, and vice versa. All right, so 11-1. Chemist wishes to make calcium carbonate, the principal component in Tums, by using the following reaction. Okay, I don't have to balance the reaction, perfect. If the chemist mixes 50 milliliters of 1.23 molar, do you remember what that big M means? Did we talk about that yet? We should have.
Concentration.
It's how many, it's molars, how many moles per milliliter, right? So we need to figure out, well, let's write them. Na2CO3 plus CaOH 2 turns into calcium carbonate, CO3, and 2NaOH. Okay, so let's back up. Do we remember what these numbers mean? This means for every 1 mole of this, there's no number, so it's a 1. For every 1 mole of this and every 1 mole of this, I'm going to end up with 1 mole of this and 2 moles of this. If they gave me the balanced equation, then all they have to do is give me one of them, and I can figure out all the other ones because it's a balanced equation. So, lots of words, blah, 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 blah. If the chemist mixes, let's use a different color here. If the chemist mixes 50 milliliters of Na2CO3, so I've got 50.0 milliliters of this, and it is 50 milliliters of Na2, 1.23 molar Na2CO3. So we did this same thing before, but they used to tell us how many moles we had or how many grams we had. Now they're telling us how strong of a solution we have. So it's with an excess of calcium hydroxide. Excess means I have so much of this, it's not going to affect my reaction. So I have too much of this, so my reaction just depends on this. How many grams of calcium carbonate, will be produced? I could figure that out too, but they didn't ask me to, so I'm going to ignore it. Okay? So if they told me that I have 50 milliliters of a 1.23 molar solution, molar is how many moles per liter. So I have to first figure out how many moles I have. If this is, so I have to figure out how many liters I'm using instead of if you can just move your decimal 3 places, or if you don't remember how to do that, then you do 50.0 milliliters. I need to figure out how many liters I have. So this has to be a true statement. There are 1,000 milliliters in 1 liter. I want to cancel out my milliliters that's on the bottom and go to liters, which is on the top. So that means I'm dividing by 1, 2, 3. So I'm dividing by 1, 2, 3. So it's 0.050 liters that I have. All right, so then if I take 1.23 molar, that means I have that many moles in 1 liter. That's what the big M means. So then I'm going to have to figure out how many moles I have. So that's easy. As long as if I have this many liters of it, I want my liters to cancel out. So I have to have this liter on the top, 0.0500 liters. So this liters is on the top, this liter's on the bottom, just so you're not confused. Maybe I divide it, I don't know. So I want my liters to cancel out. So if I take 1.23 times 0.0500, I'm gonna get 0.0615 moles. So that's back where we used to be. We used to start with, they would tell us how many moles or how many grams I had. Now they're just telling us how much of a strong solution. So if I have that many moles, for every 1 mole of this, I get 1 mole of this. So now I'm going to maybe a little bit more space. Did everybody catch that? I'm going to just give myself some more space. So I'm going to start with 0.0615 moles of Na2CO3, and my ratio is for every 1 mole of this, Na2CO3, I will get 1 mole of CaCO3. I hope you can do that math. You multiply by 1, you divide by 1, so you haven't changed it really. You just changed your label. I traded this label for this label. So I have 0.0615 moles of CaCO3, calcium carbonate, and it says that, but that's not what it asked me. It asked me how many grams of calcium carbonate I have. So I would be very lazy and turn my paper sideways so I could just keep going here, but I can't, so I have 0.0615 moles of calcium carbonate. And then how do I convert that? I want to get rid of that. And I want to go to grams. So how do I do that? I get my handy dandy periodic table. I see how much calcium is, and I don't know that off the top of my head. And I see how much carbon is and how much 3 oxygens is. And that's going to be how much 1 mole of calcium carbonate is. So maybe that's a separate step. So calcium is, I don't know, 40.1 grams per mole. Carbon is 12.0 grams. And oxygen times 3 is going to be 16 times 3. I don't have my calculator here, so 16 times 3.0 times 3. So if you add all those up, you're going to find out how many grams are in 1 mole of calcium carbonate. And I'm going to cheat and look that up. And it's 100.1 grams in 1 mole. So this unit cancels out, and I'm left with 6.16 grams of calcium carbonate. And this has 4 significant digits, but this only has 3 significant digits, so I only get 3 in my answer. Okay? So you've done this problem before, only they gave you how many grams or how many moles you had. So it's just a different starting point. Okay, but all the rest is exactly the same. Did I lose anybody? A few extra minutes. I'm gonna do this second one. All right. How many liters of a 0.2545 molar solution of sodium chloride will be necessary to make 100 grams of AlCl3? They gave me the balanced equation. So 3NaCl plus AlNO3 turns into AlCl3 plus 3NaNO3. So again, the hardest thing I think here is figuring out what are they asking me. So they said how many liters of NaCl, so how many liters of a 0.245 molar solution will be necessary to make 100 grams of AlCl3. 100.0 grams. So they want to make this in the lab. They didn't ask me about that, so I can ignore it. They didn't ask me about that, so I can ignore it. For every 3 moles of this, I'm going to get 1 mole of this. But I want to go here. I want to figure out how many liters. So it's basically the other problem, but backwards now. Now I got to start over here. So for every 100.0 grams of AlCl3, it's grams. I can't do anything until I convert it to moles. So first I have to get rid of my grams and go to moles of AlCl3. I got to figure out how much one of those weighs. My handy dandy periodic table. I'll look up aluminum. Al is 27 and Cl is 35.5, but I've got 3 of them. This is a 7. So then I'm going to add those together, and I'm going to cheat and figure out how much it is because I don't have my calculator, and it's 133.5 grams for 1 mole. Okay? So now I'm into moles. My grams cancels out. Now I'm into moles. Now for every 1 mole of these, I get 3 moles of these. So you can get an answer here. I'm not. I'm just going to keep going. And then at the end, I'll just do 100 divided, because as long as my units cancel out, I usually turn my paper this way and kill a tree for each problem and do a problem and take up a whole paper. So you could get an answer, and in the book they'll get an answer. I'm going to keep going, because now I'm into moles of AlCl3. Then I want to get rid of moles of AlCl3 and go to moles of NaCl. Well, that's this ratio here. For every 1 mole of those, I have 3 moles of those. Now I'm done with moles of AlCl. Now I can go to here. I need to figure out how many liters there are. So once this is how many moles per liter. So actually it might be easier to figure this out. So what's 100 divided by 1.33.5 times 3 divided by 1. So that would be 2.247 moles of NaCl. So then, I'm going to erase this. And I don't like red so much. I like purple. All right. So then, I want to get rid of the moles of NaCl and go to moles per liter. So, they told me that I have a 0.245 molar solution. So that means that for every 2.247 moles of NaCl, I'm going to have 1 liter of NaCl. For every 0.245 moles of NaCl, because that's what this is. This is moles per liter. So I have it on the bottom because I want the moles to cancel out. This is how many moles it is in 1 liter. So if they gave me that in molar, I can just cancel it on the bottom. So my moles cancels out and I'm left with how many liters of it I'm going to need. So I take that divided by 2.45 and I get 9.17 liters. And I have 3 significant digits there and 4 there, so my answer has to only have 3. Actually, they gave me 4 here, but then they gave me 3 there, so my answer should just be 3. So that means if I take 9.17 liters of this solution and mix it with that, I'll get 100 grams of that. Okay? So again, if I have a balanced equation, they only need to give me one thing, and I can calculate all of the other ones. And they're all the same. They all have the same format. You have to, whatever they give you, if they give you molarity, if they give you grams, you have to first get it to moles till I can get it to these, because these numbers are all how many moles I have. Then once I've converted it to moles, I go from moles to moles of whatever I'm looking for, and then I can convert it back from moles to whatever format they're asking me. If they're asking me grams, or if they're asking me the big M molarity, then that's how many moles per liter it is. Okay? Oh, look, sure. Do a couple problems, but that's how all of them are set up. So, get to moles. Use your ratios from your balanced equation. Then convert back to whatever they're asking you. And whenever I'm done with the problem, I always go back and read my question. Did I answer it the way they asked me? Don't stop here. Oh wait, they didn't ask me how many moles I had. They said how many milliliters or how many liters. If they ask me milliliters, I'm going to have to do one more conversion. Okay? All right, write me a lab for next week.